Alright, so welcome everyone. Today we are going to be doing a chemical reaction process where we are going to be producing ammonia using Aspen HYSYS. Alright, so it's a simple Haber's process we're going to be doing here. Alright, so the objective of this simulation tutorial is to guide learners through the process of modeling an ammonia production plant in Aspen HYSYS. This tutorial introduces the core concept of process simulation, including feed preparation, reaction kinetics, separation units, and process optimization. Alright, but we're just going to focus on the feed preparation, reaction kinetics, and then separation units. Now, the process optimization, we'll be discussing that in our live session. Alright, so going forward, what do you expect to learn from this? Alright, to understand general flow of ammonia synthesis, okay, learn how to define components, select your thermodynamic models, and then set up your unit operation. We're going to be simulating each step from feed preparation. Okay, not going to be working on the air and water. We'll just talk about the ammonia itself. Alright, so after we've actually separated the nitrogen and the hydrogen we need, we just go into the ammonia separation. So I'm not really going to be talking about this in this particular tutorial video. We'll discuss it more in our live session. Alright, analyze process results including temperature, pressure, and composition conversion. So we're going to be checking all of this. Alright, so if you are yet to join our tutorials, I'm going to use this opportunity to let you know that a batch is currently on. The next batch we'll be having is in October, so use this opportunity to save the date and get prepared for it. Alright, so more details you can ask in the comment section and then we'll reply to that. Now going forward, let's see what we have here. So the overall process view. So what we're going to look at is the production of ammonia. Alright, following the Haber's process where nitrogen and hydrogen react under high pressure and temperature to produce in the presence of a catalyst. Alright, so we are going to be ignoring the catalyst. We're not going to make use of the catalyst because if you want to do that, you have to start talking about loading. So like I said, this is just a simple process, alright, for ammonia production. Alright, so let's go forward. So what we have nitrogen, we have hydrogen, react in a stoichiometry of 1:3 mole ratio. Alright, we have the reaction. This is the reaction taking place. N2 plus 3H2, that's 1 mole of nitrogen reacting with 3 moles of hydrogen to produce 2 moles of ammonia. Alright, so this is an exothermic process. Alright, this is an exothermic process, and this is the energy negative, right, 92. So at this point, like I said, ammonia is ignored. It's the operating conditions for our reactor. So let's start the process. Let's start it. Alright, I already have my nitrogen, hydrogen, and ammonia selected. Alright, so going to my fluid package, I'm going to be selecting, I can make use of NRTL. Alright, I can make use of NRTL for this. I can also make use of SRK for it. Alright, so what I'm going to do is I'm going to run a simulation checking the two results. Alright, so I'll first start with NRTL, and then I think we'll compare the result for the SRK in the class. Alright, so let's go. NRTL. Okay. So after selecting that, we go under reaction, add a new reaction, add reaction kinetic, select this. Alright, so we are going to do this according to how our reaction is. So we have the nitrogen first, hydrogen second, and then ammonia third. Alright, so what we're going to be doing, nitrogen first, hydrogen second, and then the ammonia being produced. Now at this point, when we are dealing with our reactants are usually denoted in negative sign. So we have 1 mole of this reacting with 3 moles of this to give us 2 moles of ammonia. To give us 2 moles of ammonia. So our product is positive. Alright. For A, which is our frequency factor, you can see we have frequency factor, activation energy, and temperature exponent. So A, B, and B. Now remember this is also an equilibrium reaction, but we're going to be focused on the forward reaction here. Alright, so in order for us to have this, the question told us we should assume our frequency factor as 700 per second. Alright, so we are going to do this. $700, put that in. We have 92.0. Leave this at that, and then we go forward. So it said not attached to FP. Your FP means your fluid package, so we add to FP, and then we move on. Now we go to simulation. Alright, so the first thing we're going to do is to name this. This is going to be nitrogen. Alright, this is going to be hydrogen. Okay. Alright, so going forward now, we are going to be giving this the specification. Now from what we have, the temperature is supposed to be going in at 450 Celsius, having a pressure of 200 atm, so changes to atm. Alright, and then we have a mole flow. This is for nitrogen, so let's say we are making use of 100. Alright, and then for the nitrogen, the mole fraction is 1. Alright, so this stream is totally defined, and then we go on to the next stream. Now we are dealing with hydrogen. Temperature we're going to be using, we're still going to maintain the same temperature because that's what our reactor is supposed to be working with. The pressure was also going to be about 200 atm, and then the mole flow. Now this is supposed to be 3 moles of hydrogen, so we're going to be making use of 300 here, and then our hydrogen composition, we're going to make this 1. Alright, so since both of them are going into, we're going to make use of the CSTR for this as a continuous stir tank reactor. So we have nitrogen first, hydrogen second, and then we put to CSTR. Alright, so from here we get our CSTR. Where's my CSTR second. Alright, here it is. Okay, so I open it up, put in this. Now I'm going to call the vapor stream vapor VAP. Let's put vapor and then call this liquid. Alright, although based on what we are having here, we should be expecting this to be in liquid form. Alright, going to be explaining something at the end of this, so you might want to stay to the end of this tutorial. Alright, so we select our reaction. Right, the volume is not specified. We go down to parameters, and under volume, the volume of our reactor, let's say it's going to be at 3 meter cubic meter, and then from here we can check our results and confirm if we have a conversion. Alright, so there is no conversion here. Alright, we still have nitrogen and hydrogen the way it is. We are not having, ammonia is not being produced. So what do we do? Always ensure to check this. So now let's go back to our reaction set. Now this is liquid phase. This reaction is supposed to be taking place in the vapor phase, so we change this to vapor phase and then go back to worksheet, check. Alright, so we can see that in vapor phase we are having the production. Now remember, this is a CSTR, and then most times the CSTR is majorly used for liquid reactions though. Alright, but we're just trying to make use of this for the reaction process, just trying to see how it is. Alright, we're going to be the ideal reactor for this is supposed to be a plug flow reactor though, so because of when you're dealing with gases. Alright, but at the same time we're making use of the CSTR for it. It still works. Alright, it still works. So going forward, alright, so we have ammonia in our vapor stream. Now we need to bring this. Now remember, part of what we're supposed to do is to cool it. So we said reaction products are cooled and ammonia is condensed and separated from the unreacted gases. Alright, so trying to cool this, add in the cooler, put in the vapor stream. We name this cool Q for the energy stream, and then we set this to separator, so SAP, unknown delta P. Alright, so at this point we say we have about 10 atm pressure drop. And then now for us to have liquid ammonia produced, the temperature is usually below minus 33.6, so we're putting minus 33.6 here, and then at this point we have ammonia coming out from here. So let's check worksheets, composition. Now this stream was supposed to recycle it because we still have nitrogen and hydrogen in this point here, so you can still recycle this back. We have the vapor here, Alright, so let's keep going. Next thing we're looking at is the separation process. Alright, so we're going to be separating this. Now we have to sep. We call this RCY recycle. We're going to recycle this, and then we call this our ammonia. Alright, so let's check our results. So we have a flow rate of 189.8. It's higher than what we have in our recycle stream. Now let's check the composition and see what we have. So we can see that we are having about 99% of ammonia in the liquid stream, while we are having just about 1% thereabouts. We don't really have much ammonia in this, so we have more of the nitrogen and the hydrogen. That's why we say we're going to recycle it back into the process. Alright, so now we can see that this is just a simple process for ammonia production. Alright, so let me okay, simple process for ammonia production. Okay, so in our class we're going to be looking at how to simulate another reactor. Alright, and then we'll talk about how to recycle. Alright, so next time. Thank you very much.